All right. Well, hopefully this should be live now. I think there's some delay because it doesn't quite show up um, immediately. So we'll see how this ends up going. Yep, there we go. It's showing up. All right. And I'm going to check to make sure the audio is also working. So, yep, perfect. Great. All right. Our first foray into remote teaching. So we'll see how this goes. And yeah, as I mentioned, I've already kind of posted a thing in the chat where if you have any questions, please post them. And yep, already have one question there saying, oh yeah, good noon. Awesome. I appreciate it. Yeah, so the test will still be on 4/1 on April 1st. So since I've moved it back, I'm not going to move it forward again. And the nice thing is, this will be more aligned now with our previous semester. My previous semester, where we will be covering. So I'll go ahead and show you all what exactly will be on the test, and as we get closer to it, I'll kind of review this. But we will have. So on test one, or sorry, not test one, test two. We're going to have current and circuits, DC circuits, magnetic fields, and source of magnetic fields, and Faraday's law. So that may seem like more content, but current and circuits and DC circuits are kind of the same thing. So really it's just kind of 4 sections. Just like how for the first test we had weeks 1 through 4. This one we have weeks 5 through 9, but one of these weeks doesn't really count because like they're not full weeks here. So it's pretty much the same amount of stuff. Oh, so many good noons. Oh, I get so many more here than I do in class. Nice. Yeah, and I'll do my best to kind of ping back and forth between the chat and this. So that's the plan for the test, still 4/1, and I'm going to be working on those. So thankfully, it'll give me some time to make those questions. All right, so for today, we're going to kind of continue with electromagnetic induction, which is that Faraday's law, 2 names for the same thing. And so we are ready very briefly, just to remind you all and kind of catch you up where we were at last time. It's been a hot minute. We started this, and basically what this is going to be used for is the functional benefit to this is converting magnetic fields into mechanical energy. We can kind of use it for that. Or sorry, not that way around. Converting magnetic fields into electricity. And so this can be used functionally to convert mechanical motion into voltage and subsequently current. So here is kind of the quick learning objectives overview. I'm going to make this way bigger because this is zoomed out a lot. And so, yeah, I said, why does this matter? And I gave some examples: generators, transformers, inductors, solenoids, basically, again, things that convert mechanical motion into voltage and current. I very quickly had you all review electric flux, because we're going to need to use this same thing, use this concept of flux. But instead of electric flux, we are using magnetic flux. And the equation looks almost identical. This can look a little bit kind of maybe intimidating with this closed path integral, but it's the same thing as electric flux, where maybe instead of saying the integral here, you could instead write this as, because pretty much in every case that we're going to solve, the magnetic field is going to be constant, the area is going to be constant, as the magnitude of B, the magnitude of A times cosine of theta. So hopefully that looks a little bit more accessible to you. And so, yeah, the definition is just the amount of magnetic field lines through a given surface area. And the reminder is this doesn't need to be a flat plane. It can actually be a loop, which we then kind of think of as being a flat plane. So it's the amount of field lines. For instance, say I had a loop of current. Loop of wire. Doesn't even need to have current going through it, just a piece of wire. And we'll say this wire is flat with the page. And I have a bunch of magnetic field lines going out of the board. That means that this has some flux going through it. Even though this thing is not a like flat surface in terms of like if it's a loop of wire, the inside is empty, you still get a flux through it. So that's kind of the emphasis. It doesn't need to be solid. Just want to really emphasize that. And that's going to be relevant because you're not going to find any loops of wire that are a solid flat disk. So that was what we covered last time. The units are Tesla times meter squared, or I don't know if this is Weber or Weber. I'm actually not certain on the pronunciation because we never even really use this terminology. I've never heard anyone refer to it as such. We usually just use the Tesla times meter squared. All right. The next slide maybe is confusing to you. The correct answer is A. That was just because last time I wanted to give some extra points. All right. And so reminder to you all, clicker questions. I'm no longer asking those in real time. They're still in the slides. Just maybe that helps you follow it. I figured deleting it does no good. So they're still here, but we're not going to spend the time in lecture going through these. The reminder to you, and I had that previous videos and announcement saying it, to answer these questions, you now have to go, so you'll go to your assignments tab, you'll go to the clicker questions, and you don't need to do these right now. You just need to do them before next class, so before Friday's class. And you can see here 3/18/20, and I've already put a few of the questions in here. There's 4 questions, and I have to figure out how I'll do the same thing as always, where I'll give credit just for doing this and credit for correct points. I still have to figure out how exactly to do that within the system, but we're going to make it work. So same exact thing, just now you're doing it online instead of in real time. And again, you do not need to do it now. Just do it before next class. Okay. So I say that as, here's these questions, which I'm going to kind of breeze through, since they will be answered there. So the purpose of these, though, was the first one is just practicing calculating magnetic flux. You can see here I gave you the magnetic field. I gave you a loop, which is a rectangle that's 2 meters by 3 meters. And I gave you, it's a 30-degree angle. So I'll go ahead and draw this on here just for your all's, to help with the visualization of this. It doesn't have a picture of it on the web courses. So here's what it looks like. You have your loop, which is at a 30-degree angle to the XY axis, and then you have a magnetic field which points upward. So the magnetic field is going straight upwards. The hint I'll give you all is to remember when doing flux. So I'll even write all this here. Magnetic flux equals B times A times cosine of theta. This is the angle between the magnetic field and the area vector. Area vector is A. So when solving this problem, make certain you do that. Yeah, so Aaron asked, will I be doing a separate video explaining the answers? Yes, I will. I will do a separate video. That one won't be necessarily live streamed, but I will do it, and that video will get posted. I'll post that video after Friday's lecture. Yeah, so I will be posting those in the web courses, and the video for that will be posted the same place where this one is. So in the pages tab, if you scroll all the way down to wherever this one is, I just hit creation date. You see here I've now titled it lecture and clicker questions. I'll make a separate video after Friday's lesson explaining how to actually do these problems. So yeah, when doing this problem, make certain you're using the right angle. I say the right angle, not 90-degree angle, but the correct angle. I gave you this one as 30 degrees, and you have to figure out, I'll even show you what the area vector is. There's the area vector. This is the recommendation when you're doing these, so like draw the picture. It makes it easier. And the way to kind of think about this is just remind yourself, when is flux maximum? Is flux maximum when these two are parallel, or when they're perpendicular? And then that's just how many, the number of field lines going through that the most when this thing is flat, or when this thing is up and down, this thing being the plane. So in that way, you can kind of figure out what angle you should be using. Because as this thing gets flat, this angle is going to decrease. Is this angle between these going to increase or decrease? And that's kind of a trick for doing it. And I'll explain that more in the solutions. All right, and then, well, it doesn't have the person's name, Dark Mold, we'll call him that, he or she, asked if I could add some bonus questions at the end. The only challenge with that is it just takes, putting in questions into web courses it's kind of a pain, especially if I put in pictures. So I probably won't add more questions just because it is a pain to do, but I will figure out some way of giving you all participation. I'm going to make it work. So no worries there. Very likely there'll be some easy way to do that where I basically just look at it and if someone got a 0, I'm going to assume they didn't do it. Whereas if someone got any points other than that, I'll add 4. So that'll probably be the way I'll do it, but we'll see. All right. So moving into Faraday's Law, the title of this section, Faraday's Law, discovered by a guy named Faraday. Surprise, surprise, it's named after him. This is the classic with physics, is that if you discover something, you get something named after you. What's kind of interesting here, little fun fact, is it also got discovered by a separate person named Joseph Henry in 1832. And so Henry got scooped. Scooped is some jargon, I don't know if jargon is the right word, slang in the scientific or just any research community, where if you are working on a research project and somebody else is doing the same research project and publishes the results before you, we call that getting scooped, because that means that you spent all this time and they got it before you and you can't publish your results. So it's kind of funny that, I don't know how many, 200 years ago, that was still happening. And because he beat him by a year, he gets it named after him. Henry gets some stuff named after him as well, so he still gets some cred, but in different areas. So all that to say, what is Faraday's Law? Faraday's Law is that the electromagnetic force induced is equal to the negative change in the magnetic flux per unit time. All right, so we're already introducing some weird new vocab. Electromagnetic force, EMF is the shorthand for it because that's a long phrase, and the symbol for it is epsilon. And you're wondering, what the heck is that? We haven't seen that before. Basically, for the extent of this class, all you need to really think about it's basically voltage. It acts the same as voltage. We call it something different because it's generated a bit differently. Voltage we've kind of described as being a separation of positive and negative charges, whereas this is actually due to a change in magnetic flux. So because it's due to a different mechanism, it gets kind of a different name, but really it behaves exactly the same. It's equivalent to voltage. It acts like voltage. So for instance, when we start getting resistors, we're going to say epsilon equals IR, which is the same thing as V equals IR. So for all extensive purposes, you can just think about like voltage. And we just call it this kind of electromagnetic force because the result is that charge moves. And so we're like, well, why is charge moving? Well, there's a force. Well, what's the force due to? Well, it's this electromagnetic force. Again, we kind of just, it's weird. It's not really a force because clearly voltage is not a force, but we call it this weird name to just try to explain what's going on. So all that to say, the big takeaway here, EMF is voltage. And when you have a change in magnetic flux through something, so for instance, we had our loop of wire. When the magnetic flux changes, you actually generate you generate this EMF, this voltage, and if you have voltage, you get current. So changing the magnetic flux results in this kind of voltage that causes a current. And that's where we get this is how we convert from magnetic fields into current. All right, so this is actually turns out nicely. So we're at the 11:45 mark, which is, as I mentioned, I'd lecture for 15 minutes, give a 5-minute break. and then lecture for another 15 minutes. So what I will leave you with in this break is I want you all to think, what are the 3 variables in magnetic flux which can vary in time? And I say vary in time. Which are the 3 variables in magnetic flux basically that you can change? If you can change them, that means it takes time to change them, so they're changing over time. But what are the 3 variables in the magnetic flux equation? So yeah, spend the next few minutes thinking about that. If you have any questions regarding either anything we've covered or anything just outside of this, feel free to post in the chat, and I'll kind of be looking at this in the time. Otherwise, feel free to kind of take a break, review some of the stuff that maybe I've covered so far. These slides are all available online, so you can kind of just spend some time, digest, and we'll be back in a few minutes. All right. And yeah, so I may play around with this break time. I don't know if 5 minutes is the right amount or less, but I want to definitely give you all who are listening some time to kind of process, because I know it's going to be harder to focus on a screen for longer periods of time, and I'm not having as much kind of interactive back and forth as we do in class. So I want to give some time for kind of work with that. So, all right. So I'm getting a lot of questions on the test I'm seeing. So the plan is for the test to be basically just more questions, and there'll be multiple choice. There won't really be any way for me to do partial credit, unfortunately, because I'll continue to think maybe I'll try to brainstorm how to do that, but I can't think of any way to do that effectively. but we'll see. We'll see with that, but I will be looking at the test scores. I will make adjustments as needed. And yeah, I'm going to make certain that the tests, I'm not going to just be okay with everyone getting a 60 on that. If needs be, I'll adjust the scores to make it so the test is actually measuring accurately. I'll probably give some boost to scores just with the assumption that if there was partial credit, you'd get some points back. So, so moving on to this, what are the 3 variables which can vary with time? So let's go ahead and look at our flux equation. So magnetic flux equals B. So this is pretty much the form we're going to use. The magnitude of B, the magnitude of the area vector, which is just going to be the area of the plate, times cosine of theta. And so Melinda asked, is it the angle, the normal vector, and the magnitude of the magnetic field? And that is completely correct. If we just look at this, there's 3 variables, B, A, and theta. B, A, and theta, where theta is the angle between B and A. So, this is kind of the considerations if you think about this from an engineering perspective. So let's go back to our, let's write that EMF equals negative d theta dt, magnetic flux. We look at this and we say, okay, how can I generate this EMF, this voltage? What 3 things can I change? Well, I can either make the magnetic field stronger or weaker. I can make the area increase or decrease. Or I can make the angle between the magnetic field, an external magnetic field, and the area of the loop change. I'll go ahead and tell you that the one that is going to be used the most in the real world is the angle one. Because think about it, that literally just means, so here's my loop. Let's just say the magnetic field is originally going this way. It's very easy to rotate this loop. It's very easy to design something that rotates a loop. It's difficult to make something that makes the loop get bigger or smaller. And making the magnetic field, the external one, bigger or smaller, you could probably do that, but that's a little trickier. And that would, that'd be unusual. Maybe like have a magnet that moves back and forth. This is the easier way. This is the way that pretty much every generator works, is you rotate it. We rotate the angle. Okay. So again, a lot more discussion on the test. And again, as I think about it more, we'll see. We'll see what I can do. It's going to be a lot more brainstorming. And once I kind of settled it down, I'll definitely let you all know exactly what the plan is. Okay. So here's an example problem that I'm going to work through for you all. It is, what is the induced EMF in a circular loop of wire, which has a radius of 2 meters, if its area vector is originally parallel to magnetic field and the magnetic field changes from 4 microtesla to 2 microtesla in 5 seconds. Okay, so how do we go about solving this problem? Well, we're trying to find induced EMF. So if we're trying to do that, you need to immediately jump to this equation. All right, and you see here I put the negative. That negative we're really going to use that later when it's more of a conceptual piece that says that it's going to make a flux, it's going to make a current which opposes it. And we're going to kind of get to that a little bit later. We're going to kind of talk about that more because basically, so I'll get through this problem, then I'm going to spend a bit more time on that. But mathematically, it's that negative change in flux. And the negative, again, just tells you really what direction the current's going to flow. So we'll spend a little bit more time on that in a second. So let's just say our d dt. Pull that derivative out and plug in the flux. It's the magnitude of B, the magnitude of A, times cosine of theta. So this is how you're going to set up every single problem where you're trying to find induced EMF in some loop of wire. You're going to set up this derivative, and you have to look at, okay, what is changing? What is changing in my problem? So I gave you a radius of 2 meters. I gave you that the area vector is parallel to the magnetic field. If they're parallel, that means that theta is going to be 0. And we have a magnetic field initial, which is 4 e to the minus 6 Tesla, microtesla. Micro is to the minus 6. And the final magnetic field is 2 e to the minus 6 Tesla, and this occurs over 5 seconds. So once we write out our variables, it's pretty straightforward. What is the thing that's changing? It's the only one that has an initial and a final. So we look at our equation, and we basically pull out the things that are constant. We pull out the area. We pull out the cosine of the theta. And we're just left with the change of the magnetic field with respect to time. So we plug in what those are. It's a circular wire, so I'll go ahead and draw this picture here. There's my magnetic field. There's my area. There is my radius. And so since it's a circle, our area is going to just be pi r squared. We already said it's cosine of 0. We already found that angle before. And the change in magnetic field with respect to time, we assume, unless I say otherwise, and I'll go ahead and tell you every problem I gave you, it changes linearly. So basically we can just say 4, make sure we put our negative there, 4 e to the minus 6 minus 2 e to the minus 6 over 5. The final magnetic field, oh, I have this backwards. We want to do final minus initial. I'll even put this here just to make it B final minus B initial over time. So then just negative pi r squared. Let's start plugging in values actually. Pi times 2 squared. Cosine of 0 is 1. And then you just get 2 e to the minus 6 minus 4 e to the minus 6 over 5. All right. So I have to go run and get my calculator. All right, and we plug that in. So we have pi times 2 squared times 2 e to the minus 6 minus 4 e to the minus 6 divided by 5. All right, and we get a very tiny number. We get our EMF so it ends up being negative because 2 is less than 4. 5.02 e to the minus 6 volts. Remember, the unit for this is volts for EMF because it's basically the same thing as voltage. So there's our answer. There's an example problem with this where and you can see here it's tiny. It's like, what is that going to do for you? Not very much. That voltage is minuscule. And so we're going to see later on some examples of how we could generate a larger voltage. Okay. Now, I mentioned this before, this idea of the negative sign. Basically, and I don't think, I'm going to kind of mention this now because we're not going to really say it later. The question is, which way is, so there's the voltage, which way is current going to flow? And this is where the conceptual kind of challenge comes in. And let me just double check to make certain. Oh, no, we're going to get to that later. Okay. Sorry, we're going to get to that later with Lenz's law. I'm not going to deal with that now because I have some nice slides which give the wording for it. So for now, we're just going to say voltages like this, and later on we're going to find the direction that current would flow due to this voltage. But just to prime you all, this negative sign matters. We're going to use that for that. Okay, so here's the clicker question I gave you all, so this one says a loop of wire is shrinking from 3 meters to 1.5 meters. Its radius is shrinking over 5 seconds. Area vector is parallel with the magnetic field, and the magnetic field has a magnitude of 4 microtesla. So to this problem, I'll go ahead and tell you, ignore the negative sign. You see here, there's no negatives. Don't worry about whatever negatives or positives you get. Just take the magnitude of it. The sign doesn't really matter with these kind of problems. Okay. So you're going to be doing a very similar thing. Here, our magnetic field changed with respect to time. Here, something else is changing with respect to time. I'm going to leave that to you all to figure out what that is, and I'll post that video with the solution later. All right, with our last few minutes, I'm going to kind of just cover some last little bits with this. So how do we actually make a large voltage? Again, if we see here, I already mentioned 5 times 10 to the minus 6. That's lousy. You can't do anything functional with that. So how do you actually generate a large voltage? Well, if I have one loop of wire, that's how much it makes. But what if I put another loop on top of that? Well, now I have 2 loops, and I've basically doubled the amount of voltage, because you could treat these as 2 separate problems, a loop and then the exact same loop, and so each one would get the same change in flux, generate the same voltage, and so it would be voltage 1 plus voltage 2. So EMF total equals E1 plus E2. They would just add up. So then imagine a third one, and a fourth one, and a fifth one. And all those voltages are going to add up. Another way to think about it is you literally increase the amount of area, because each loop has an area, and each one's independent from each other. And so the long and short of this is that if I have a wire that instead of just one loop, maybe it's a loop that I've made 5 loops on top of each other. You just multiply the change in flux through one of those by the number of loops. So if I had 3 loops, N would be 3. If I had 5 loops, N would be 5. And so, for instance, in that previous problem, we could make the voltage 5 times as strong by making 5 of those same coils on top of each other. Engineering-wise, you'd want to make these as tightly packed as possible, because if they were separated, then they'd experience different magnetic fields, and you wouldn't get as strong of an effect. And you need those wires to be insulated, because otherwise you just get if you took a bunch of wires that weren't insulated and you packed them very tightly, you effectively just made one big fat wire. So you need them to be insulated so they each act independently from each other. And this could be one wire that is like coiled. Again, imagine a slinky that you maybe compress really tightly. If you insulated that slinky, that's kind of a good visualization for what this would look like. It can be one wire that just kind of coils, keeps coiling, keeps coiling, keeps coiling, keeps coiling. And that's fine. So the big takeaway physics-wise is if you have multiple loops, you just multiply your change in flux through one loop by the number of loops. Engineering-wise, there's a few more considerations. All right. I'm going to conclude with this rotating loop, and that'll kind of be the last thing I talk about today. So we mentioned there's 3 variables that you can change to get an induced EMF. It was the magnetic field, it was the area, and it is the angle between the magnetic field and the area. I went ahead and told you all that that change in the angle is the easiest way. And so what would it be? So let's go ahead and just derive it. EMF equals negative change in flux with respect to time. Well, we're going to go ahead and plug in, do that same d dt of B, A, cosine theta. In this problem, we assume that these two are constant. We're saying, okay, the magnetic field is constant, same direction, same magnitude. The area is constant. I have this loop. I'm not deforming it. I'm not making it bigger or smaller, but it is rotating. So the angle is changing. So you get negative B times A times d dt of cosine of theta. So this is just a derivative. We take the derivative of this, and you have to use chain rule. So we get negative B times A times, take the derivative of the inside, you get d theta dt, because we're taking the derivative with respect to time. And then you have to change it to sine. So take the derivative of the inside, take the derivative of the outside. And there you go. That's what it is. It's interesting here because we get this additional term, which is d theta dt. And this so you can see on the next slide, it's the same exact thing I just did. Oh, and I forgot to put, if you had multiple loops, you'd put an n there. So, and capital N is the number of loops. Just covered that. Number of loops. And this d theta dt is omega. That's the variable we're going to use for this. Omega And a reminder to you all, this is the angular frequency. Angular frequency or angular velocity, they're both two different ways of saying the same thing. It is the rate of change of the angle with respect to time. If it spins faster, you will generate, well, depending on where it's at, you're going to generate a higher peak of this. I'll show you all next time what this kind of graph will look like of the EMF. It's not a constant value. It actually changes because the angle changes. While the spinning, how fast it's spinning may be constant, the angle will constantly be changing. So you actually get an EMF that looks like a sine wave, where this is my theta. Well, this is with respect to time, and this is your voltage, or in our case, EMF. All right, so that is everything for today. That is all we're going to cover. May not seem like I got through too much, but this is pretty much what we would have gotten through in a normal class period. Pending maybe a couple more things. We had a lot of logistics to talk about. And so, yeah, next time, let me recap everything we've covered. We covered Faraday's law. We said Faraday's law is the thing that generates a voltage based on a change in flux. We worked through an example problem with that, and we then identified, if you have multiple loops, and we saw that when the angle is changing, you actually get a significantly different equation where you get this omega, this change in theta with respect to time. So next time I'll do a quick example problem, and we'll go ahead and move on to Lenz's law next time, which is to figure out the direction of the current. This clicker question is also in there. There's some questions here that are related to the content. Some of the questions are review questions. As we move through the semester, I include these because I also want you all to be remembering the content we've already covered. So that it's going to be a combination of questions on new content and questions on older content, just because at the end of this course, the goal is that you've learned everything in it, not just what you most recently learned, not just the stuff we covered at the end of the semester. So that is that. Reminder, I have office hours today as usual from 1 to 2 p.m. Those will be through Zoom. So if you have any further questions, please join me for that. Otherwise, concludes it for today. All right, thank you very much.